Okay, good morning again, everyone. Today we are going to continue data structure for computer graphics, and we are going to start talking about texture mapping. Let me continue where we left off last time on Tuesday. So this is data structure for computer graphics. We have talked about how we represent individual meshes, so how we can store meshes efficiently by using indexed faced structure, which was just listing the vertex information separately, then the triangle information, giving an index to each of the vertices, and using these integer indices to identify triangles. And it saves a lot of redundancy. And for each triangle, we can also have or for each vertex, for that matter, we can have other information like the material, normal vector, pre-computed and stored along with the vertices. Now, I started talking about oak-tree a little bit and mentioned bounding volume hierarchy and KD tree. Today we are going to go over the remaining of the slides and finish these data structures for graphics, which are specially called acceleration structures. So here, a quad tree in 2 dimensions and oak tree in 3 dimensions is actually a regular subdivision of the space. So it's more space-oriented division, not object-oriented. In other words, objects in our scene, for example, it just divides in the middle of the space. And in oak trees, for example, at every or in quad trees in 2 dimensions, at every branch we divide the entire space into 4 quadrants, and for each quadrant we either have a subtree or we have a leaf node if that quadrant only contains a single object. If it contains a single object, if we have in a quadrant, if we have a single object, we just discontinue dividing that space into 4 again. So it may not be, depending on how your objects are distributed in the environment, you can see that this is not a balanced structure, not necessarily balanced, but its depth is still going to be logarithmic in the order of, your precision. Dividing, for example, if your coordinates are always integer, and if you're not going to divide more than a single integer while you're dividing, whatever the minimum and maximum values of any x, y, x's are, it's going to be log base 2 of the difference between max and min. Okay, so its depth is still going to be very small with each time we are dividing by 2. So logarithmic in terms of the precision of your space. And also, it also depends on how objects are distributed in the environment. So number of objects all do matter, but it may be the case that all the objects are arranged, or all the trees are arranged in a kind of a linear fashion. So it may be a highly imbalanced tree, but still it will give you some logarithmic complexity of space. This is in 2D. An oak tree is a direct extension of quad trees into 3D, where we divide the space into, again, octants this time. Each of these major planes, xy, xz, and yz planes. So there are 3 major axes. Each pair of these axes define a plane, a major plane, and each time we divide by, in the first case we are dividing by major planes, but in the subsequent divisions, as you can see, we are actually dividing the octant into suboctants by using planes that are parallel to the major planes. For example, if you see this, let me annotate here. So I can change my pencil, yeah. So if you look at this part, this axis, this plane of dividing, this plane that divides this octant into 2, is actually parallel to the YZ plane, where this is the Z-axis, this is the Y-axis, this is the y-axis, and this is these two axes define the YZ plane, and the one that is dividing the small cube into two rectangular prisms. And actually, since we're going to be dividing simultaneously by using other planes that are parallel to the major planes as well, it's going to be cubes. Each of these entries will be cubes all the time, smaller cubes. Each time we're dividing by 8. And this division continues adaptively as long as there are more than one objects within an octant. Okay, so this is how quadri. The implementation details, we are not going to go into implementation details of these, but you may find lots of resources on the internet about the implementation details. So, okay, I will stop annotating. Where is my delete? Oh, okay. And so, yeah, quad trees. And there's another important data structure which was made popular by the first-person shooter games in the early in 1980s or early 1990s is binary space partitioning. So if you look at the quad tree here, this is quad tree always divides by axis parallel planes or major plane parallel planes when it's dividing. So when your object contains lots of irregularities, and there will be lots of divisions around those irregularities like this, it doesn't actually make use of the topology or the orientation of the object's plane itself. So on the other hand, in binary space partitioning, we are free to choose any dividing plane, not necessarily a plane that is parallel to the major planes. So each time we are choosing in 3 dimensions, we are free to choose any plane in any orientation, and usually a plane that, or a polygon, which defines a plane. A polygon in your scene, for example, lies on a plane. A polygon's plane may be used as a separating plane. And here the branching factor in binary space partitioning trees is, as the name implies, it's binary. Every time we choose some arbitrary plane and divide the entire scene into 2 regions. Here's an example of binary space partitioning. I think it will be good to analyze this in this example. And the main reason binary space partitioning was used was not for our ray object intersections. Actually, it can be used for ray object intersections, but they can also be used to sort the objects, not sort, but to maybe render the objects in back to front order. Okay, so this is really good. If you have a binary space tree representation of the scene, you can, for example, immediately when you're rendering the scene, by traversing the binary space partitioning tree in some order, you will guarantee that an object that may occlude some other object, that may hide some other object behind, is going to be rendered last. There's an algorithm called Painter's algorithm, in which when you're rendering the object, so painters, when they're painting a landscape, for example, they start by first drawing or painting the farthest objects first, because then they continue painting closer objects on top of farther objects. Because if you first draw an object that is in front, drawing around its boundary, if you want to draw something at the back, it will be difficult to do that. So this back to front rendering or drawing of objects, and by the way, when we're drawing objects with binary space partitioning, in terms of distance, they're not necessarily sorted, but the way the binary space partitioning is constructed, it guarantees that when you render an object here by traversing this tree in some order, you're guaranteed that there will be no occlusions for an object that is, the back to front rendering will be satisfied. So, and then an interesting property of this is you may actually have your camera, you can view the scene from here Okay, your eye will be maybe here, or your eye may be here. It may be in any one of these locations. Still, you can use the same BSP tree while you're rendering, and it will always render in the correct order. And the rendering order, traversing the binary space partitioning, works like this. So we basically know where the camera is, right? I mean, the camera position is given before we traverse this tree. So what we do is, it has to, each binary space partitioning node contains a dividing hyperplane. In 3 dimensions, it's a dividing plane. In 2 dimensions, it's a dividing line. Okay, so this is a 2-dimensional example. So we have lines that divide the space into half spaces, half planes like this. In 3D, it will be half spaces when we use our plane. To divide the scene into two, it will be 2 half spaces. So, but given this divider, so every node contains what the divider hyperplane is. In this case, this line information is stored along with the node that you're currently in. So you start with the root node and you have this plane. So if you know your eye position, you can ask this question, whether your camera is to the right or to the left. So each one divides the entire plane. If this has a front face, if this line has a front and back orientation as in planes, we can actually figure out whether the camera is in front or the back of this plane. So the idea is this: we are going to traverse a tree in such a way that first render all of the objects at the back of this plane and the other side than the camera. So first render all these and then render everything that is here. So it will guarantee that the camera, depending on if the camera was here, for example, if this is where our camera is, then in the rendering order will be in such a way that draw this part first and then draw everything that is here. So that's the way to traverse the tree, and we do this recursively as we move along the tree. For example, if this is camera 1, for example, we are rendering with respect to camera 1. So what we do is we say we first render this left subtree, for example, if these two objects are in the left subtree. So we first visit this one during traversal, and then visit this one at the second order. We are going to visit the right subtree next. Visit the subtree that is not on the same side as the camera. Okay, so I'm rendering with respect to this camera now. So when we come to this one, we see that there is another divider here, which basically says, again, with respect to our camera, although this dividing line only divides the half plane that is here, we treat them as if it divides the entire plane. And ask the same question again with respect to the camera's position. Whether the camera is on, if the camera is on this side, again, render the objects that are on the other side first. So the rendering order will be, let me change the color now, this will be rendered first, because then we come to the leaf node. There is no dividing line here. Render this object, then render the object on the same side as the camera. This will be rendered second. Then we move to the other, so when we are recursively traversing this tree, when we are done with the child nodes, we come and return from this function, and so the left subtree is entirely visited. We now visit the right subtree. In the right subtree, we see that we're at an intermediate node. There's a dividing line here, so it says render the objects on the other side first. So this was our camera. The branch that shows the other side is this branch, so we visit this branch first. And again, according to this plane, it breaks the recursion is broken when we hit a leaf node, when we hit an object. But the way that, I'm just, for example, currently explaining if we have the binary space partitioning tree already, BSP tree already. The way we construct the tree is sometimes these dividing planes may chop the objects into pieces. So it may be actually parts of objects that are in one branch and the other. So for example, if it's a single triangle that we have to break with a hyperplane like this, we break this into a triangle and a quad, which appears as two separate objects on two parts. But what you're coming to your question, you're right. At the leaf nodes, we may assume that there is a single object. The tree is constructed in such a way that all the leaf nodes contain single primitive objects. So when we hit that object, we just render it, and we break out of recursion. The recursion is like this. When in an intermediate node, if it's not a leaf node, there has to be a line there. We just say we compare this line with respect to our camera point, and first visit the recursively render the subtree that is on the other side, then recursively render the subtree that is on the same side as our camera. So it's just two recursive calls inside the function. And when we come to the leaf node, we exit that. So when we come to that, there's this dividing line, and we see that the camera is on this side, so this one is rendered next. So this one is going to be number 3 that is rendered, and this one is, then we break out of recursion, visit here. This is going to be rendered as the 4th entry, and then this single remaining object, the purple one, is going to be rendered last as the 5th object. So this is going to be ordered. This 1, 2, 3, 4, 5 will be the order of rendering for a camera that is here. So as you can see, the way we traverse this BSP tree ensures that 5 is rendered last, and it's in the same cell as the camera. It may not be the closest one. I mean, it may be the case that, for example, 5 is here, 4 is here, and the camera is here. As you can see, 4 is closer than 5 to the camera, but we are not actually computing the distances here. If it's in the same cell, rendering 4 first will not have any effect. I mean, we are going to render 5 last, but it's 4 cannot occlude 5. That's the critical point, okay? Because it's in the same plane here. An object that is here cannot occlude, cannot be in front of an object that is on the same side as the camera. So that was a really nice data structure. And the way people use this for efficiency is they use the, for example, this is especially good for if you have a first-person shooter game, which is composed of levels where there are rooms, lots of rooms, in which when you're inside a room, for example, all the other objects in the other rooms are not visible. So you can actually directly traverse the BSP tree so that you come to your room and render only the objects in your room. For example, in this example that I showed you, it gave us a rendering order in which we rendered all the objects. But what if these divider hyperplanes actually correspond to some walls in our level which are not transparent? In that case, you don't need to even, for example, if currently the player is here, you don't need to even visit the subtree that is on the other side, because it will be impossible to see those objects that are there. Implementation-wise, depending on what type of operations you're going to do, for example, binary space partitioning is not, I believe, is not used for ray tracing that much. It's good for this back-to-front rendering, or it's good for filtering out objects that are not going to be seen anyway. I mean, if you have, depending on your scene organization, if you are indoors of a very large building, for example, and all these divider planes are actually walls that are occluding other objects, then it may be really good to implement binary space partitioning to get rid of, to not even send these objects to your rendering pipeline at all. So you can just filter these out and focus only on a particular cell. You'll find implementations of all these on the net, which they're all very similar to each other. They contain a tree-like structure, which is recursively subdivided, recursively traversed. Each of these, sometimes these subspaces in BSP, for example, the area that they contain is really irregular. in that case, when you're trying to have a ray intersection with your cell, it may not be very good to intersect your ray with this arbitrarily oriented polyhedra. Instead, if we had just axis-aligned rectangles or rectangular prisms or cubes, it will be better to do ray and region intersection would be easier. So I think in ray tracing, BSP trees would not be preferred that much. In Octree, the space division is done regularly, always from the middle of the current space. So if you have if it's going to be done by checking if there's an object in subspace. And the way we do that is, implementation-wise, let's think about this. For example, how can we determine when in an octree, for example, when we are in a cube, how can we determine whether this cube contains a single object or not? I think this could be done at every iteration. For example, in the first iteration, we can actually we are not doing all the objects. Each time, for example, in the first level of the octree, when you divide it into 8 regions, all the objects, for example, you can just check the x-coordinate. If your objects are sorted by their x-coordinate, okay, you may immediately divide your object set into 2. Actually, it's divided into 8 subsets. So when each time you're going one level deeper, you're actually dividing your entire set of objects among these 8 regions. You don't have all the set of objects as you go recursively into these sub-regions. You can just say that, okay, these objects that have x-coordinates smaller than 0 with negative x-coordinates, you go to this branch. You recursively, so in other words, in your recursive octree computation, you send to your recursive function the set of objects that are going to be used for that region, for that octant. So the ending of recursion could just be like this. For example, imagine you have this function build octree, okay? It may get, for example, the boundaries of your rectangle or cube, so min x, min y, or max x, so all these 8 numbers, sorry, not 8, 6 numbers here, min y, min max y, min z, max z, so it shows the boundary of your octree to build in the first place. And another thing is you have this, maybe the set S, which is the set of objects to build the octree upon. And the ending of the recursion could just be done by looking at the size of S. For example, you can just have if s.size is less than or equal to 1, and that's it. Create a leaf node, return. No recursive function. Yeah, so, but if s size is greater than 1, you need to, after you divide it into regions, at this point, your code should also be responsible of dividing this S into 8 different subsets and calling recursively for each subset, you're going to call the build octree function recursively for that divided set. And so therefore, you'll be keeping track of which object is where, and this is how you will end the recursion. Yeah, I'm glad that it's clear. And yeah, in BSP trees has different versions. Sometimes, actually, this is the example. Where's the camera here? Assume the camera is at point C. So yeah, when the camera is in point C, it was here before. Now you can see that the rendering order is different. This 1, 2 is still like that. Because if this is the point C where the camera is, the first thing that is going to be rendered is going to be 1, which is not actually the farthest object, as you can see, but this 3, 4, 5 are on the same side of this plane. So here, if we render 1 first, it's impossible to occlude anything in 3, 4, 5, because 3, 4, 5 is in the same region as C in terms of this, with respect to this hyperplane. Or in this case, it's in 2D, it's with respect to this line. So C is also on the same side of 2, so we render 1 first, then 2. If we come to this one, 5 is on the same. We render so the dividing line is first this one, so render everything that is on the other side, render 3 first, and then we come here, we have this dividing line, render everything that is on the other side first. 4 is rendered, and the last thing that is rendered is the object that is on the same partition, same cell as C. So how do we create a BSP tree in the first place? As I said, there are different approaches for that. One thing is we just select a random polygon and create a plane aligned with it. But this is not how game developers did when they built their BSPs. This was not a random polygon they selected. They selected, for example, according to the floor plan, they selected the walls as the separating hyperplanes, as separating planes. So this is how they use it. It may be, and we put that polygon in our root. We separate the other polygons into 2 sets, just like Octree, where we separate everything into 8 sets. We separate the other polygon into 2 sets, depending on whether they are at this, depending on which side of this separating polygon they are in. So during creation, we actually spend some time to partition our set into subsets, and we recursively call our build BSP or build Octree function recursively on these partition sets. And if our plane intersects some polygons, we split them. The example I showed you, if it's a triangle, for example, it can be split into a triangle and a quad, or it may be the case that if the separation is at some vertex, it may be to 2 triangles. And we send them to their, we just put them into their corresponding sets, and we recursively apply these steps until, again, just like Octree, until a certain region contains only one object, one primitive object. We continue doing this recursively. So this one is an example. So this ABCD, as you can see, there are line segments. So our scene, so this is an example from Wikipedia, how we construct this BSP binary space partitioning tree on line segments. ABCD are our line segments. We choose A to be the separating hyperplane. So sometimes we can have objects also put into the root node along with the plane itself. We can say, for example, if there's an object on the plane, let's also put it here. So the order is going to be like this. First, I think these will be the objects that will be rendered last. First, render the objects that are on the other side, and they are on the same side of the camera, or actually they may be rendered second. So in terms of their ordering, this is like a in-order traversal in which the root node objects should be rendered. If there are any objects that are in the plane, on the plane itself, these are objects, for example, that are on the same side as the camera, they will be rendered last. But as you can see, the hyperplane here, A, actually divides everything into 2. Line B is divided into 2 line segments. Line segment B is divided into B1 and B2. D is divided into D1 and D2, C1 and C2. So all the line segments are divided into 2 parts. Now we recursively call for B1, D1, C1, which is on this side of the plane of the line. We call recursively again on them. And in this case, for example, for example, in this example, B2 is chosen as the separating one. B2 divides D2 into 2 parts, D2 and D3. C2 is on the same side as D3. So recursively it goes like this. And this step continues until we have only one line segment in a region. Yeah, and until we have, as you can see, I think it's beneficial to keep the set balanced. The tree, if the tree is balanced, so how can you make the tree balanced to choose hyperplanes in such a way that it's like the median I think it is beneficial if you have a binary space partitioning tree. If you choose your dividing planes in such a way that roughly half of the objects lie to one side and half on other side, I think that will be good. The smaller the depth of the tree, the more efficient your traversal is going to be. But if you're going to render all of the objects, if you use this tree to filter out some objects completely, like these hyperplanes are like non-transparent walls, I think it's really beneficial to make the tree balanced. But if you're going to render all of the objects in your scene anyway, the computational complexity will not change. Whatever the number of nodes in the tree is, you're going to still spend the same time, right? So it will not matter whether it's balanced or not. Again, this depends on how you want to apply your BSP tree. But if you're using BSP to filter out entire regions of the scene, indicating that that part is not visible anyway, because my separating hyperplane is something that occludes everything that are on the other side, then the other side of tree could be completely filtered out, no traversing that part of the tree, and then it will be beneficial to have it balanced. I think I'm sure if you research the literature on this, you'll find tons of papers which deal with maybe about how to choose the separating polygons in BSP trees, or BSP trees for certain types of scenes, for indoor scenes, for outdoor scenes, BSPs for scenes that contain transparent objects. So this is really, there are a lot of variations. So this is just a basic idea that we are giving you in this course. KD3, I mentioned about KD3 actually last time. It's just similar, it's very similar to octree, but we alternate between these three major planes each time we're dividing. It's a 2D tree. It's actually, when I say 2D tree, it's a binary tree. So a KD tree is a binary tree in K dimensions. So there are variations of KD tree even in higher dimensions, like 5, 6, 8 dimensions. It's an index structure for multi-dimensional data sets. So any point, for example, you may use KD tree to build an index on your set of points, or in this case it may be on the set of your primitive objects, triangles and spheres. So each time we divide. Here again, if you want to build a balanced KD tree, the divider hyperplane is chosen in such a way that it passes through the median object, the object with the median x coordinate or y coordinate, depending on which hyperplane you are currently dividing with. Okay, so in order to ensure the tree is balanced, we can actually slide the it's not always at the middle of the space. It may actually pass on an object, which is, if in those sets of objects you have in that subtree, you may choose the hyperplane in such a way that the set is going to be divided into roughly 2 equal subsets if that hyperplane is chosen. So yeah, each node is a k-dimensional point here. The split, it's very similar. The idea is similar to octree, but the splitting planes, there are 2 major differences. One of them is its branching factor is 2. The splitting planes are from depth to depth. We alternate between the splitting planes. And the other difference is that we choose these hyperplanes by choosing the median object. And when I say median object, with respect to the x coordinates or y coordinates, depending on which hyperplane we are dividing at that point. So it will, if it's a balanced tree, the depth will be again logarithmic in terms of the objects this time. So this is not space oriented, but object oriented. The division is done with respect to the objects, and similar to BSP tree in that regard. Because if we choose the dividing hyperplane with respect to the objects we have in BSP tree, in KD tree we do something similar. So here's some code from again Wikipedia. I think this is the build KD tree algorithm. So a name like this, KD tree, just the name KD tree, actually is a very bad name. So there are usually two basic operations when you have a data structure, an index structure. You have to provide two basic algorithms. First one is how to build the data structure given on a set of points. So how to build an index structure on your set of points. The other is how you query, how you use it for a query. So query algorithm and construction algorithm are two separate things. How you traverse the KD tree for some special purpose. I think this is a building build KD tree or construct KD tree algorithm, as I see from the source code. So it's exactly like this. So we choose the axis based on the current depth. So at every recursion, what we do is we increase depth by 1 so that the subtrees are going to know which depth they are. When we first run this, we run it with depth 0 or depth 1, depending on whether you have 0 at root node or 1 at root node. And then it gets a point list. And as you can see, the point list are, so the median is selected, the median point by this x or y coordinate or z coordinate is selected from the point list. We create a node. And the location of the node, the dividing hyperplane, is at the median, and the left child and right child of this node is in such a way that, as you can see, the first parameter of this function becomes the roughly half of the points go to as the first parameter to one recursive call, and roughly half the other points go here and return node. So this one doesn't show actually how we end recursion. For example, we should have on this pseudocode, we should also have a function that says that if point list dot size is equals 1, if it's equal to 1, return a leaf node constructed, and this point is put into that node. Okay, so this is a KD tree on points. We can do similar KD tree on triangles and spheres on any scene. But yeah, that's termination of this recursive function call is missing from here, as I see. So if the point list size is 1, just don't call recursively and end your recursion at that point. Here's an example. If we randomly divide here, I think the expected complexity still be balanced. I mean, the depth may still be log base 2. It may, so sometimes randomness, its expected behavior may be very close to the balanced, close to the best case. So that's not a bad idea to randomly divide. If we have leaf nodes here, we may have leaf nodes with no object. When we randomly divide, in that case, again, we stop recursion. Yeah, either if the point list may contain no object, then at that point we can also create a empty leaf node at that point. That may be possible if you randomly divide. Yeah, I mean, even so here in your termination, you can write if it contains more than one object, then do the division. Therefore, the division will be 1, 1 or 2, 0. If it contains less than or equal to one object, we stop recursion. So yeah, at that point, we will, if we have a point list with empty point lists, we don't do, we just create them. We may even return null. We don't even create any node for empty point lists. So this one is an example on which we build a KD tree on 6 points. So there are 6 points, and here some points, for example, this point 7,2 is actually stored along with the node. So when we choose some point as a divider with respect to the x-axis, so since there are 6 points, there are 2 medians actually. both this one or this one could be chosen as the median x coordinate, so y2 is chosen. And when we choose a point, in this version, for example, of the KD tree, the points themselves may be stored at intermediate nodes as well. In some other versions of KD tree, you may see that we just put the dividing lines equation here, which is equal to x is equal to 7. So x is equal to 7 is the line that we have here. And the point itself actually may be put somewhere on the points, maybe at the leaf nodes in some version of KD trees. If you see in some versions that the points actually, all of the points are at the leaf nodes, it's just a variation of KD tree. Don't think that is some different kind of a data structure. So these are all small implementation choices that you may make, whether to store the points also along with the intermediate nodes. And I think this is the bounding volume hierarchy is the last one that we're going to talk about. So KD tree partition space into disjoint regions. Here, there's in bounding volume hierarchy, the index is built on objects. Really, the space is not divided into huge regions at all. It's like we hierarchically represent our objects in the scene. So KD tree, we still divide the space in choosing the space subdivision with respect to objects position. Still, I told you that this is an object-oriented division, because in oak tree we divide the space. Even the space division is done with no objects in regard. It's just divide everything from the middle of the space. In KD tree we still divide the space, but by taking into account objects' coordinates, so that this we have roughly equal size of objects on the both sides. But in bounding volume hierarchy, it's the space subdivision is actually, there's no space is not subdivided. The objects actually are. We build an index directly on the objects. We first contain every object hierarchically within bounding boxes. This is done hierarchically like this. For example, you may have several objects in your scene. Let me turn on annotate again. So this one, I don't know. It's really slow in terms of selection of pencils. Anyway, so if we have, for example, an object here, an arbitrary triangular shape, a sphere, another object here, we may have multiple objects here. So the first thing we do is we first bound each object in some kind of a tight volume. Whatever type of bounding volume we choose, our goal is to make it as tight as possible, okay? Because if we don't make it tight, it will not be a very good representative of the object behind. There will be, for example, there will be some false positive, because we will be using these bounding volume objects to say, for example, when we have a ray intersecting with this bounding volume, potentially it intersects with the object behind. So the tighter it is, this potentiality becomes like a certainty if you have a tighter bounding volume. So the bounding volume should be a simple object like this, a rectangular box or a sphere or an ellipsoid, whatever bounding. When I say bounding box, it refers to a rectangular prism. But this bounding box could be, for example, bounding volume, in which we can use spheres or ellipsoids or ellipsoids. So any type of some regular, easy to intersect ray, we are going to intersect our rays with them. Another thing is, after I have these objects bounded by these volumes, I can also actually hierarchically, iteratively provide large bounding volumes to sets of these objects. Okay, so in the second level, for example, I can have these green bounding boxes, and at the root level I can have this pink one or purple one as the root node. So this is the hierarchy. This is what we call hierarchy for It's hierarchically, objects are grouped together in these, and as you can see, it's not the space that is divided. It's like objects are grouped together in a hierarchical manner. So here's an example of that. This is the large bounding box, and the main purpose is if the ray doesn't intersect the entire bounding box of these objects, it's guaranteed that none of the objects are going to be intersecting. Okay, so this is like when there is no intersection, we can completely filter this box out. But when there is intersection, this may still be a false positive intersection, so you can have a ray that passes through this bounding box but intersecting none of the objects. That's possible. This will be like a false positive hit in this case, but by making these bounding boxes as tight as possible, our goal is to limit these false positives. But still, it provides very good speed up, and the bounding volumes can actually overlap. When we have these bounding volumes, for example, this volume is bounding these three objects, this bounding box is bounding these three objects, and as you can see, there's overlap between them, and that's no problem with us actually, it's because we're not dividing the space into two. When we are doing the compare ray object intersection, it may be possible that our ray intersects with both of the bounding boxes. In that case, we will continue traversing in both of the subtrees. Okay, but if there is no intersection, we can eliminate an entire subtree. Traversal of an entire subtree can be eliminated if there's no intersection at all. So it may go all the way down to individual primitives, triangles, or spheres. Just these parts are really similar to other ways we construct objects. Here's an example bounding volume hierarchy. Again, if we choose to group the objects every time by 2, for example, if you start with the entire set, and then half of the objects are in one bounding volume, half of the objects are in other bounding volume. So if you always divide by half like this, it will be a balanced tree. An array missing an entire bounding box, we can filter out completely the objects that are contained within that box. Okay, so that's the idea. An array may intersect with multiple bounding boxes. In that case, again, I told you that we continue recursively traversing the bounding boxes underneath those. So here, the intersecting, this one intersects, then we continue here, and we come to the lower part, we see that our ray doesn't intersect with any of them, and then we skip these. So this object does not intersect with any real object. So even it may be the case that we may go to the leaf node, our ray intersect with the bounding box of this red triangle, but when we do the intersection with the triangle, it may not actually intersect. But the thing is that we avoided intersection test with these 3 triangles and with these 2 triangles as well. When we group objects, if they have 10K independent faces, how can we group them? Even a single group, for example, you can first group them by object, for example, a 10K triangle, an object, for example, but there's a single object. Yeah, so I understand your question now better. So if we are rendering, for example, a single object with 10,000 triangles, how can we group them? What I would do is, for example, I would just find, just like maybe I can combine ideas from bounding volume hierarchy with octrees. For example, for that single object that I have, first I'm going to encapsulate the entire object inside a rectangular box by finding its minimum, maximum extent in all these 3 coordinates, x, y, and z. So this will actually, even the single box will provide lots of speed up, because a lot of the rays, they don't intersect with anything. These black regions of your image, actually they are rays that don't intersect with anything, and it has the background color. But even for those pixels, you spend a lot of time in your ray tracer, right? because you intersect every Revit, the entire set of your triangles in your scene. Even a single box will provide lots of speed up. Okay, so by just providing a rectangular box between this min max of your single object. Yeah, and also, but so this is just this. There is no hierarchy here. How can you provide hierarchy here? By borrowing some ideas from oak tree. After you have your, or KD tree, after you have your min and max, I can maybe have a lower bounding box in which if I divide my object, my triangles in the middle at between min x plus max s divided by 2. I can now have another rectangular box which is smaller. So I think this can be done like that. So there is an algorithm, as Mujalla mentions here, Ritter's algorithm, for finding a bounding sphere. And we can do that. If we have multiple objects in the scene, we can have a bounding box for each object and combine them hierarchically. But in order to go to triangle level, we need to just partition the triangles of our objects in such a way that half of the triangle, 10,000 triangles are in one bounding box and half the other. And you don't need to chop your triangles into pieces if you're when you're dividing your triangles. I don't think it will matter that much. If you decide on certain bounding box, let me actually try to draw it here, or maybe on GIMP. So what I'm trying to say is this. After you decide on some boxes, okay, for example, you have decided these two boxes that are not overlapping. For example, this was your min x and this was your max x. And imagine you have an object that is like this, okay? And lots of triangles in between. We may have lots of triangles in between. What I want to say is that when you're deciding on which triangles go to which object, it's not very difficult to, for example, you have a triangle here. You can look at these three vertices. If any vertex is inside this box, checking whether a vertex is inside a box is very easy. Just checking the coordinates, x coordinate, whether it's a min x, min y, y coordinate is between min y, max y. If it's inside a box, just put it into that box. And it may be the case that, for example, you may have a triangle here in which part of it is inside this box, part of it is inside this box. I don't think it will make it very inefficient to duplicate this triangle and put it in both boxes. Okay, I mean, for objects that are at the boundary, you may just duplicate them and have them represented in both boxes. You'll be testing maybe 2 times for this intersection, but the amount of savings bounding volume hierarchy gives you is so huge that these duplications will not matter that much. You don't need to think about making it difficult, chopping of triangles. You don't need to think about those. And here is a traversal algorithm. We are out of time. I'm just going to quickly finish the remaining set of slides. We have like 3-4 slides. So the traversal, it's really easy. We just test with the box first. If it's false, we just cut out of recursion. If it intersects with the box, we then our box has 2 parts. So this is actually the bounding volume hierarchy. This box is like probably a data structure with left and right children. So with this rec1 and rec2, so we hit left and right. So we just basically continue traversing on the left box and the right box, and we get the intersection from both boxes. Whichever is close, we return it from our function. And so this one shows how fast it is. So this is the horse and mug scene, which contains 32,000 triangles, or all of them triangles except these 2 spheres, 32,000. And when we use no bounding volume hierarchy, it takes 12 minutes to render this in this resolution with 8 cores. And if you use bounding volume hierarchy, you can reduce this 12 minutes to 1.2 seconds on the same machine. So this one just shows how fast bounding volume hierarchy, how fast speed up a bounding volume hierarchy can provide you, from minutes to seconds. So 60 times speed up. Okay. So we finished this part. We didn't have time to start texture mapping, but we are going to start talking about texture mapping next Tuesday. So about data structures for graphics, these are all the things that I want to discuss on data structures on computer graphics, for computer graphics. Do you have any questions? Okay, thanks everyone for attending. I will stop recording now.